Welcome back. So this week we're going to continue with our study of light by looking at geometric optics. Optics is the scientific study of the behavior of light, and we spent our last unit looking at the wave-like properties of light. But now we want to understand how light forms images. In order to do that, we will start by looking at mirrors. So in this picture, we see that light bounces off of a lake, and it results in an image that looks exactly like the mountain, only flipped upside down. So we'd like to understand how does this happen. To start with, we want to study plane mirrors. So plane as in a flat mirror, P-L-A-N-E. The first thing to remember is that light rays travel in a straight line. A beam of light or a light ray, they all mean the same thing. They move in a straight line. So if you want to see something, you need a direct line of sight in order to see it. Remember, in light, the electric and magnetic fields, they are oscillating, but the light itself is traveling in a straight line. So if we shine light onto a flat reflective surface, like a mirror, and let's start by shining the light straight down at the mirror, the light would bounce straight back towards us. If the light is bouncing off at an angle, then the light will bounce off of the mirror, and then what we do is we draw a line normal to the mirror. So this normal line is perpendicular to the mirror, and the angle between the incident light and the normal line is equal to the angle between the reflected light and the normal line. This is called the law of reflection. Theta I is equal to theta R, where we call the incident light the ray of light that is hitting the reflective surface, and the reflected light is, well, the light that is reflected by the mirror. So this is probably the easiest equation we've run into in this course, but you do have to remember that the incident angle is the angle between the normal and the incident ray, and the reflected angle is the angle between the reflected ray and the normal. So I think in your clicker question, it kind of tricks you by giving you the other angle, and then you have to figure out what's the angle between the normal and the ray of light. So this is what we call specular reflection. So in specular reflection, you have a flat surface and the light bounces off cleanly. The other kind of reflection is diffuse reflectance, or reflection. In diffuse reflection, the reflecting surface is rough and it's not flat. So while each of the individual rays of light follow the law of reflection, the angles are all different because the normal line is different. So it still follows that law, but since the normal line changes, you end up with no image, just kind of a generalized sort of color of the surface that you see. So what happens when we see an image? Well, if I hold up an object, say a pencil with an eraser, light reflects off of the eraser, and a few rays head towards your eye. The point is that these rays of light emerge from a single point, and they all come from that point and go into your eye. Once those rays hit your eyes at different points in your eye can then resolve them. But the point for the moment is that an image comes from a point where many rays of light with the same origin emit in all directions. So if you trace the rays of light back to the origin, you find the source of the image. So when you were looking at a pencil or something, it's pretty straightforward. But what about a mirror? Right, mirrors are pretty fascinating, and you've all seen your reflection. What is happening here? Well, here we show some flowers, and if you look into the mirror, you can find a set of rays of light that leave the flower, bounce off of the mirror, and then into your eye. Because the mirror is nice and flat and highly reflective, it looks almost exactly as if the flowers were behind the mirror. The reason for that is if you followed the rays of light from your eye and wanted to see where the lines converged, it would be behind the mirror. So to your eyes, the object seems to be behind the mirror. This is what we call a virtual image. A virtual image is an image that comes from somewhere that there is no actual light ray. The image seems to come from behind the mirror, but there's no actual light ray there, so that's why it's called a virtual image. Let's look at an example where a person is taking a picture, and we want to know how large of a mirror is necessary for them to be able to take a picture of their entire body. It's useful to define a few terms here. First, the distance of the object is the distance between the mirror and the actual object whose reflection we're interested in. This distance is positive, and for mirrors we will consider the distance to be positive if you are on the real side of the mirror. We also want to know the distance to the image. This is the distance where the image appears to be from through the mirror. The image is on the other side of the mirror, and so we will consider the distance to the image to be negative. Since the mirror is flat, The distance from the mirror to the person and the distance from the mirror to the image are the same. It's also useful to note that the height of the person and the height of the image, so we'll call these h sub o for the height of the object and h sub I for height of the image, and with a flat mirror they are also the same. Now we want to see how large of a mirror we need to have so that we can see our entire body. So to do that, what we want to do is we want to follow the rays of light. The first ray of light is parallel to the ground and it travels to the right where it bounces off of the mirror. The incident angle here is 0 degrees, so it bounces back at 0 degrees directly where it came from. Next we follow a ray of light that points towards the bottom of the image. Notice that if we also show the reflected ray, the angle will be the same as the incident, and it will point directly at the woman's foot. Now notice that the distance between where the ray hits the mirror is exactly half the height of the woman. You can tell this by the ray making an isosceles triangle, where the angle at the top and the bottom are the same. So the purpose here is to introduce a few ideas. One is the idea of an image, where the light appears to be coming from, and the corresponding distance from the mirror to the image, and the distance from the mirror to the object. Also, the height of the object and the height of the image here have been introduced. So, I guess we should just conclude a bit here. So an image in a plane mirror appears to be the same size that it actually is, although the left and right are flipped, although up and down is not. And the size of the image is the same. So this is only true for flat mirrors, so we're going to start talking about curved mirrors next, so there we're going to have some magnification. Okay, so you have a few questions, and next we're going to talk about spherical mirrors. Good luck.